All right, today's topic is from 1.6, inverse functions. What does inverse function mean? What does inverse mean? That there are things that undo each other. For example, 2 plus negative 2 equals 0. These quote unquote undo each other. The notation for function inverses, the notation for inverse function is f prime of x. That is not a -1 exponent. It's the notation that your inverse is opposite. So that's the notation. It means inverse. So what it means to have an inverse function is the domain of the original. So let's say I have a domain of the original and a range. I'm just picking some random points. The domain of the original becomes the range. And the range of the original becomes the domain. So this is f of x here. This is my function. And then this is my inverse function. The domain and range switch places. We're just going to front load some vocabulary, and then we will practice some of these. If two functions are inverses, then the compositions, notice it's plural, compositions must equal x. Now, if you're given the graph of the inverses, or if you're given a graph, you can determine if the inverses or if the functions are inverses. They have to reflect over the line y equal x. There's y equal x. So here's 1, 1, okay, 2, 2, etc. So if I have this function, and it has to reflect over y equal x, it's going to have a mirror image on the other side. That's how we know from a graph that they're a function. What we're going to do first is we're going to verify if two functions are inverses. I'm going to verify if two functions are inverses. Okay, so 2x cubed minus 1. We said to verify, we have to find the composition of the function. So I'm going to take g of x, and I'm going to put it into f of x. So I'm going to find out of f of the cube root of x plus 1 over 2 is equal to x. So let's substitute that in. 2 times cube root x plus 1 over 2, but that is being cubed minus 1. Well, a cube of a cube root are inverses. They undo each other. So let's do this then. 2 divided by 2 is 1. So now I have x plus 1 minus 1 equal x. So yes, the first composition equals x. So now we have to go and compose it the other way. G of f of x. So now I'm going to put f of x into g. g, so that's cubed minus 1. So now let's substitute it into g of x. Cube root 2x cubed minus 1 plus 1 divided by 2. So now I'm taking the cube root, 2x cubed is 2. 2 divided by 2 is 1. So that's the cube root of x cubed inverses. Therefore, since both compositions equal x, they're inverses. If you compose them and you get any other result besides x or whatever variable it is, then it's not an inverse. All right, let's look at the next one. First, in my head, I have to ask, why are they telling me that my domain is restricted to greater than or equal to 0? It has to do with this. We know that that function is restricted because it's a square root. But to verify, we need to put in the square root of x minus 1 into f of x. So I'm going to compose f of g of x. So that means I'm going to take the square root of x minus 1, and it's going into my function. Square and square root are inverse functions. They undo each other. So that's x minus 1 plus 1, not inverse functions. They're inverses. Okay. So that one equals x. So now I can move on. Now I'm going to compose g of f of x. So I take the square root. What is f of x? X squared plus 1 is f of x. I substitute in for x minus 1. Now I'm looking at the square root of x squared. Well, those are inverse operations. They undo each other, so it equals x. So are they functions? Are they inverse functions? Equal x, equal x. So yes, they are inverse functions. We just verified that. Okay, so that's how you verify it if you're given two functions. Let's look at some pictures. I have to determine graphically if the two functions are inverses. Is this a reflection over y equal x? Well, let's see. Boom. So let's look. Okay. Yeah, it looks like it. So yes, all the points in red are reflected over y equal x in green. So it's a direct reflection over y equal x. So yes, the functions are inverses. You'll want to know for sure how to do this if it is a reflection or be able to describe this. Okay, so here's my y equal x on my second graph. Let's just take any of the lines. Let's take this line first and see, does it reflect and give me this line? Well, if I look at it and I tried to fold my paper over y equal x, I'm going to get something that looks like this, wouldn't I? As a reflection. So since these two lines, since this and this are not the same, these two, whoopsie, these two functions which are the black lines, are not inverses because they do not reflect over y equal x. Okay, So we can verify that they're inverses. We can determine from a graph if they're inverses. Now we need to know, can we find an inverse? So let's look at this. We did this in Algebra 2. Okay, so first step, step one, we want to change the f of x to y. It just makes our math easier and a lot less messy. Step two, we want to switch the x and y. So let's do those first two steps. Step one, change the f of x to y. This is step one. Step two, switch the x and the y. Now we're going to move on to step three, which means solve for the new y. So I'm going to add 9 to both sides. I'm going to divide now by a -4. Okay, in standard pre-calculus answers, we don't necessarily like negative numbers in our denominator. So what I can do is if I divide this positive x by a negative, it can become negative. If I divide this positive by a negative, it'll become negative, but now that's a positive. So that's step three. Is it the same answer? Look, this is a -1/4. This is also a -1/4. -9/4. If I separate out my fractions, -9/4, -9/4. So it's the same value. Step 4. Change the y back to f of x, or f prime of x. F prime of x equal -x minus 9 all over 4. Okay, then it says to determine any domain restrictions. Did I have any domain restrictions in my function in here? No, those are all real numbers. So there was no domain, it's all real numbers. The range was also all real numbers. Let's write that as a range. It's also all real numbers. The output. If I flip it, remember by definition inverse, the domain becomes the range, and the range is this true. So the domain is also all real numbers. Is this also true for the inverse function? Yes. Okay, so we have no domain restrictions, and we're good. So now we're going to move on to another one that's in a little different format. Okay, so step 1, change f of x to y. Step 2, switch. Step 3, solve. Okay, so I'm dividing by 2, so to undo, divide by 2, I multiply both sides by 2. And I would get 2x equal 5 minus 3y. Subtract the 5. Divide by a -3. Now I'm going to fix it when I come over here in step 4. So step 4, here, the f prime of x equal -2x plus 5. To put it in that standard notation that people like. Okay, so here's a polynomial. By taking, I just would have two fractions. If I divide both of the 5 and the -3, this is just a polynomial. So this domain, all real numbers, range, all real numbers. Now can I flip that over here? Okay, so the range becomes the domain. Is that true? Yes. The range becomes the domain. Is that true? Yes, that would be true for both of those. Last problem. Okay. Find the inverse algebraically. Well, this function, we can go ahead and find it algebraically, and then we'll talk about the domain restriction. So step one, rewrite. Switch. And solve. So I'm going to square both sides to undo the square root. Add 3. Divide by 2. And then rewrite. Now we have to talk about domain and range restrictions. Okay, so the domain, we've talked about this. It has to be greater than or equal to 0, since I can't take the square root of a negative number and come out with a real number. So that's the domain. The range then, we know, cannot be a negative. This range, the output will never be negative, but the output could be 0 or positive. So we can say that our y's are greater than or equal to 0, our domain and range for the function. Now, if we have an inverse function, what happens? The range becomes the domain, but domain is not y's. The domain are the x's. So I have a domain restriction of x greater than or equal to 0. My domain becomes the range. So I have also a range restriction, but range is using the letter y. So we have determined that because our first function is greater than or equal to 0, the domain and the range, then we switch them, so we have a domain and range restriction on our inverse function as well.